Hello everyone, welcome to the third lecture on finding the roots of equations. So last two lectures we looked at bracketing methods, the bisection, false position, we looked at graphical approach, and we said that we would mainly use this for kind of estimating the initial guesses. And then in the last lecture we looked at two open methods, we looked at fixed point iteration and the Newton-Raphson. Today we're going to look at secant and modified secant, which both are kind of based on the Newton-Raphson method. And the main difference is in the Newton-Raphson, you're required to find the derivative. So in the secant method, we estimate the derivative instead of finding the actual true derivative for the function. How do we do that? We use the backward finite divided difference approach, which is derived from the Taylor series. So the Newton-Raphson itself is derived from the Taylor series. Then we use also Taylor series to estimate the derivative, and then we come up with a new equation. So this is the estimate for the derivative. If you remember, it needs 2 points. So f of xi minus 1, and xi minus xi minus 1. In this case, it's flipped. Why? Because we're finding 1 over the derivative. So this would be your equation that is going to be called the secant method kind of equation, or that's what you're going to apply when you're applying the secant method. And you would apply this for many iterations, starting either at x equals 1 or x equals 0, 1, 2, 3, and so on. So that's the secant method. Actually, one more thing to note here. So in the secant method, we're approximating the derivative, and we're using this approach. How do we ensure that this approximation of the derivative is accurate? So to minimize the error, we minimize step size. So in this case, the point xi and the point xi minus 1 should be close to each other so that you get a good estimate of the derivative so that the method actually works, right? You're estimating the derivative, you don't want a bad estimate. So you want to make sure this step size is really small. So again, the secant method is an open method. So we don't necessarily have to bracket the root in our first 2 points, in xi and xi minus 1. They don't need to bracket the root. The whole point of having 2 points is to find the derivative. It's not to bracket the root, okay? So that's an example here. So they're trying to find the derivative at xi. So then they took xi and they took this point xi minus 1, which is somewhat far away from it, right? But that's what's used in this diagram. And then the real root is found right here. So again, we want to make sure that the distance between this point and this point is small to get a better estimate. Now, even if we estimate an accurate derivative, it doesn't mean that we're going to actually get the true root. Why? Because the Newton-Raphson does not always converge. So just like the Newton-Raphson, the secant method also can diverge. All right, so both of them can diverge, and it depends on that initial guess. How far is it from the root? What's the kind of, how nonlinear is my equation or function? Okay, and that would affect how accurate or if the method's going to converge or diverge, just like we saw in the previous lecture. So the secant method is good, but what's better is the modified secant method. Why? Because it controls how far away is that second point by using a factor which is called the small perturbation factor, symbol delta, and by picking a very small value for this factor, we control kind of how far away is my second point all the time, making sure that it's a small distance away. So this factor here typically is a value less than 1. Okay, it'll be maybe 0.1 or 0.001 or 0.0001, okay, depending on how many significant figures or how many decimal places can you do in your computer or calculator. So basically what we did is we estimated the derivative, but instead of taking 2 points, we took this initial point, and then the second point is basically xi plus the small factor multiplied by xi. So instead of starting with 2 points, we just started with 1 point, but then we also identified this factor, which is a small number. So we need to kind of start with 2 things compared to the secant method. So we do that, and then we find the derivative, and the step size here is delta xi. Why? Because if I look at, 1 point is xi plus delta xi, the other one is xi. Subtract the 2 from each other, we get delta xi. So that's the step size. So it's a very small step size, and because of that, we have to make sure when we calculate f of x, we take a lot of significant figures. Because if I take a very small step size, the actual change in the function will only be visible after so many significant figures. So we plug this in to the Newton-Raphson and we get this equation. So xi minus f of xi, 1 over the derivative, which is basically this equation flipped. All right, so that's the modified secant method. So we'll do an example here. So this example is the same function that we had in the previous lecture, where f of x we made equal to 0, and the function was x squared minus x minus 1. X naught here is the initial guess for the root. Delta here is that small perturbation factor, which we're going to pick as 10 to the negative 6. So we take the modified secant equation, that's the equation. X naught here is going to be what? 2. F of x naught would be f at 2, and then this delta would be 10 to the negative 6 multiplied by 2, and so on. So we can plug this in. We see that 2 is here, minus f at 2, 10 to the negative 6 times 2, and so on. We find a value of 1.67. If you remember from last class, the root was around 1.618, right? So that's pretty close. So that's one iteration of the modified secant method. So we can do a second iteration where we take this x1 and then we use it in the second iteration. So now, instead of seeing 2's everywhere, now we see 1.67 everywhere. Okay? And then we still have that factor, 10 to the negative 6, up here and then down here. We do all the math, we find that we get 1.62, and then you can basically continue this way. So now you would use the 1.62 in the next iteration, plug it in, do the math, then you find it. So here we see the Newton-Raphson that we solved last lecture, or I showed you last lecture, compared to the modified secant. Here we see the true percent relative error, all right, here and here, versus the number of iterations. What's the difference between these two? Nothing, right? Why? Right, so the fact that we picked is 10 to the negative 6, meaning that our estimate for the derivative is pretty accurate. So the Newton-Raphson requires you to find the derivative. Modified secant doesn't. We applied it, and we used a very small step size, and because of that, our estimate of the derivative was really good, and basically there was no difference between the two, right? So you can see here pretty much the same for this given problem. All right, so now we're gonna do an example. First, I'll give you guys some time to try it out. All right, so here we have a tank. Okay, so it's a spherical tank that can hold water in a small village in a developing country. The volume of liquid it can hold can be determined using this expression. So this is the volume of the water inside, so that's V, equals to pi times h squared, where h is the height or the depth of the water in the tank. So you can see in the diagram here. So for this given depth of water in the tank, h is this distance. multiplied by 3 times r. R is the radius of the spherical tank. Then you have h again, and then you just divide by 3. So this is the function. Now the problem says, if the radius is 3 meters, what depth must the tank be filled so that it holds 30 meters cubed? So it's telling you, say you have a gauge that tells you the height in the tank, how deep is the water, but it doesn't tell you what's the volume. And you want to know, okay, when is the volume 30 meters cubed? At what height is it 30 meters cubed? Use the modified secant method with an initial guess of 1. Okay, so this initial guess is not going to be 0. Why? Because 0 doesn't make sense, right? I mean, you want to find when the tank is filled with 30 meters cubed. You're not going to say it has 0. So you use a number that makes sense, okay? The factor here, delta, is 10 to the negative 6 again. How many iterations does it take to get less than 1% relative error? So that's the first part of the question. Second part is, do you think it's possible to use the Newton-Raphson instead? So try this out. Try this first part of it. And I'll give you a few minutes and let's see how far you get. So let's take this up together. So this is lecture 2.3, slide 8. So the problem has this equation, which is volume for the tank, equal to pi h squared multiplied by 3r minus h divided by 3. In this given problem, the radius is what? 3. So r is equal to 3 meters. What else is given? Volume, right? So the volume is 30 meters cubed. To solve the root of this function, or to find h, we need a function where we want to find the root. So it's going to be f of h, or we can call it f of x, okay, for simplicity. So we're going to say this is f of x, or you could have said also, you could have also used h, okay? So what's f of x going to equal? One? What's f of x?
Pi 3r h.
So you took this term and you multiplied it with this?
The right hand side, 30 by the right hand side, then divided another 5, then divided another h.
Okay. Okay. To find the root, you want the equation to equal 0. No, you remember from last class, we said we rearrange the equation so that the function, okay, is equal to 0. Because that's where we're going to find the root. Okay, that will be the solution to the problem. When the function is equal to 0 is our solution. How do we make the function equal to 0? We move whatever's on the left to the right side. Simply. So we're going to subtract the volume from both sides. Okay? So this is the function which should equal to 0 if h is correct. So if we found h, where h will give us the volume of 30, this will equal 0. Okay? So pi h squared, we're going to say 8x squared in this case, multiplied by 3, where r is 3, minus h, which we're going to say is x, divided by 3 minus 30, where 30 is the volume. So now that's the function, and in the problem it's given that our initial guess, x naught, is 1. And the small perturbation, delta, is equal to 10 to the negative 6. The modified secant equation, again, is derived from the Newton-Raphson, where we estimate the derivative. And the function is x1 is equal to x naught minus f of x naught multiplied by delta x naught times f at x naught plus delta x naught minus f at x naught. So x1 is equal to what now for the first iteration? 1 minus we substitute, right? So we say f at 1, where we plug in 1 to this function, multiplied by 10 to the negative 6 times 1, and then f at 1 plus 10 to the negative 6 times 1 minus f at 1. So I'm not going to do, I guess I'll plug in, I'll show you what the numbers are for the first iteration. So we're going to have 1 minus negative 21.6224,196. Okay, here it's going to be 10 to the negative 6. Here it's going to be f with that small step size. So it's going to be negative 21.6224,039. So you see the difference starts after the 4. If I didn't take this many significant figures and I subtract here by this number, what do we get? 0. So it won't work, right? So you got to make sure you use enough significant figures for the problem to work. So here we're going to subtract negative 21.6224,196. You do the math, you're going to find that x1 is 2.3765 meters. So that's the estimated depth of the water in the tank where the volume would be 30. If we look at the percent relative error, what are we comparing here? So we're comparing this value to the previous, which is the initial guess, which is 1. So we do the math, we find that this is 57.922%. So not less than 1%, so we need to continue. So now we go to x2, where x2 is going to be basically a function of x1, right? So it's going to be x1 minus f at x1 multiplied by 10 to the negative 6 times x1, f at x1 plus 10 to the negative 6 multiplied by x1 minus f at x1. So what's x1? 2.3765, right? So we use that in the next iteration. You do all the math, you find that x2 is 2.0374. Percent relative error, where we compare this value to this value, is going to be 16.644%. So we can see that we went from 57 or 58 to about 17. So we are approaching 0. So it's so far so good. We are converging. Let's do one more iteration, and you'll find that x3 is equal to 2.0269 meters, where the relative error is 0.52%. So less than 1% at this point. So how many iterations did it take? to get to less than 1? 3 iterations, right? So we can say, therefore, it took 3 iterations to drop below 1% relative error, or you can say percent relative error, where in this case we're going to explain the result. Okay, so we say a height or depth of 2.0269 meters should give a volume of 30 meters cubed. Does that make sense? Any questions? So the second part of the problem says, do you think it's possible to use the Newton-Raphson instead? So what's the condition that we need for us to use the Newton-Raphson? So can we find the first derivative? Let's see. So using Newton-Raphson, so the function f of x is pi x squared 3 times 3, which is 9, minus x divided by 3 minus 30. So that was the function that we came up with in the beginning, where we're trying to solve for the root. So let's multiply this out and see what we get. So this is pi x squared multiplied by 9 divided by 3, right? So that would be 9 times 3 divided by 3, sorry. Minus pi x squared multiplied by x divided by 3, right? So this would be, instead of x squared, would be x cubed divided by 3. And then the last term is minus 30. And then we can rearrange this so that we can write it in like proper polynomial form, where the largest order is on the left side. So in this case, we can write this as negative pi x cubed divided by 3 plus what? 3 pi x squared minus 30. So looking at this, you can clearly see that you can easily find the derivative for this given problem, right? So here, f prime x is equal to negative pi x squared plus 6 pi x. So this is the derivative, and then therefore the answer would be, therefore you can use Newton-Raphson, and you don't have to solve it. All right. Did you guys cover roots in the lab yet? Not yet, yeah? So just heads up, in MATLAB, if you want to represent a polynomial, typically you look at the coefficients of that polynomial and you put that in a variable. So let's call that variable a, and a would be the variable with the coefficients of my polynomial. So this is my polynomial. So what's the first coefficient? Negative pi divided by 3, right? So this would represent the coefficient of x cubed. What's the next one? 3 pi. So this is for x squared. What's next? We have to put the 0 in y. So MATLAB knows this is a third order polynomial. Okay, because if we put only 3 numbers in there, it's going to assume it's second order. So we put the 0 in, and then the last thing would be minus 30, right? So that would be my variable for polynomials. And then to solve for the root, there's a function called roots. and you say roots A, where A is the variable for the coefficients, and then MATLAB will spit out answer equals 8.6139, 2.0269, negative 1.6408. Why do we have three roots? It's third order, right? So it's a cubic function. It's got three roots. At least this one has three roots. So now you get the job of identifying which one is the actual answer, right? So looking at negative 1.6408, can that be the height or the depth of the water in the tank? No, why? Because it's a negative. How about 8.6139? Can that be an answer? So we have a spherical tank. The radius here is 3. That means the diameter is 6. This is larger than 6. So it's impossible, right? It's too large. So that means our answer is 2.0269. And if we compare that with what we got up here, it's the same number. So if you wanted to do your work and then check, did I do this properly? You can use MATLAB if you wanted for your homework or your project or so on. All right, so any questions? No questions? Okay, so we move on with the slides. Here what I have is basically the graphs that I kind of showed you last class, where we see the estimated root over the different iterations. So here initially, it was estimated above 2.3 and then went down to closer to 2. And then as you can see here, by the third iteration, it's pretty much not changing much when we applied the modified secant method for this given problem. Here we see the relative error. So initially above 50, then between 10 and 20, then close to 0, right? So less than 1% by the third iteration. And then pretty much after that, really close to 0. Here we see the true relative error. Again, 50, 10 to 20. Here it's still not 0. Why? Because there's probably a lot more decimal places that we skipped, right? So, and the true that we're using here probably has more significant figures than what we used, and hence we're not going to have the exact answer at 3. But as you move on, you would. And then here we see this graph where this line is our function, which is f of x equal to 0. And the dots represent kind of the result from every iteration. All right, so if you recall, like the first iteration was closer to 2.5, so we see that here. Then second was closer to 2, and then you can see the kind of lighter color here, the third iteration in there. So it was relatively easy for this method to find this root, because you can see in this region, at least between 1 and 3, our function is somewhat linear, even though the function is a cubic, right? So making sure your initial guess makes sense, right, and close to what you would think is the true value. And to check if your answer is the true value, what you do is you take that root that you estimated, plug it into this equation, and check what volume you get. If the volume is close to 30, that means you've done your work properly, okay? Most cases, I won't tell you to check your values, but if you wanted to on a quiz, you can check it if you have time, right? If you're like, you have time, you want to check, then you can. All right, so that is the last slide. So we covered all of the methods for root finding in this course, right? So we looked at the bracketing, looked at the graphical, we looked at the open methods, And we said that bracketing methods always converge. Open methods don't necessarily converge. Sometimes they diverge, sometimes they converge. Today's lecture was focused on the secant method, where we said if I want to apply Newton-Raphson and I can't find the derivative, then I want to use the secant method. Okay, so that's the main advantage of the secant method or the modified secant method.